Hello, everyone. My name is Mohammed Attahir Jibril from the Technical University of Ilmenau, and I'm going to give a report of what we have been doing and our considering a hybrid OLTP-OLAP graph benchmark. So we've been working on a PMEM, persistent memory-based graph database, which exploits the characteristics of persistent memory to accelerate graph processing. So there are a couple of design decisions that we've made in view of the peculiarities of PMEM. For example, obtain DC persistent memory modules make use of a write combining buffer of 256 bytes. So we store data as in persistent tables, which a table is a linked list of chunks, which is of multiple of 256 bytes and is cache line aligned. Another consideration is the overhead of dereferencing persistent pointers. So we avoid making use of persistent pointers as much as possible. Instead, we make use of offsets for accessing records. There is also allocations and deallocations in PMEM is expensive. So we make use of group array allocations, and instead of deallocation, we reuse blocks of deleted records. We make use of a bitmap for the management of free space. There are other data structures that we employ, like persistent dictionary, which we use to outsource properties in order to make chunks and records of equal sizes to allow for accessing records using 8-byte integer offsets instead of persistent pointers that are 16 bytes. We also have a hybrid index that keeps inner nodes in DRAM and leaf nodes in PMEM to improve lookup performance. So this is a short overview of our storage architecture, which is optimized for PMEM. And we've carried out some performance evaluation of our PMEM-based system, a DRAM version of our system, as well as a disk-based graph database. We considered different scan types, and as our query workload, we made use of the LDBC SMB interactive short read queries, as well as the interactive update queries. The main message we get from this evaluation is that a system that is well optimized to exploit the characteristics of PMEM can achieve a near DRAM performance, as we can see in this figures, especially for the index lookup, which minimizes access to PMEM. We've published this year in eDBT. So afterwards, we also considered the LDB-CBI queries in the context of graph query recovery. So the question is whether to recover a query, especially a long-running query, after a failure, or to restart it afresh. So the considerations is in recovery, it entails storing intermediate results, as well as storing the state of a query before failure. So upon recovery, you recover the intermediate result, and then you continue execution of the query where it stopped. On the other hand, restart entails wastage of computation, especially if the query involves heavy aggregation, joins, and so on. So this is the trade-off that we investigated using a couple of BI queries. And the factor that we've identified that determines whether or not it pays to recover is one, the point of materialization, the point on the query pipeline where you materialize your intermediate results, and also the level of query progress just before failure. So it makes more sense when a high percentage of the query has been executed to recover than if the query fails at the beginning of its execution. We've also published this this year in Damon. It's a short paper. You can look into it if interested. So having considered the SMB interactive short read and interactive update queries, we also, and as well as the BI queries, we thought of taking a look into an OLTP-OLAP graph benchmarking. There exists already a hybrid benchmark for relational databases, the CH benchmark, which is based on the TPCC and TPCH benchmark. So we thought of using it as a starting point and to adapt it for graphs. So we started with a couple of designs to realize this hybrid OLTP-OLAP graph benchmark, starting with the schema design. So first, we introduce unique IDs because you don't have foreign key references anymore. To have this flexibility that a graph model offers, we introduce unique IDs similar to the IDs in the LDBC benchmark. So each node of the same type has a unique ID. So there's also a trade-off or a consideration of whether to make a table, a relation as a node, or to model it as a property, to just push it into the as a property of another node if you want to push it out of the topology. So what we've come to realize is it's an optimization between storage and performance, to some extent, the level of traversals, edge traversals. So one thing we did was we merged a history table, for example, into the customer table and then modeled this as a node. We also merged the new order node as a property of the order, the new order table as a property of the order node, because we do not need to uniquely identify these entities in the queries. There are other considerations that we did, which we took from the CH benchmark. There's a common entity between the TPC. So on the right hand side is the TPCC schema. This is the TPCH schema. The customer and order tables are common to both. So like the CH benchmark, we took the TPCC to be the base schema, and then we appended the relevant aspects of the TPCH to it. There is a suitable mapping between order line of the TPCC to the line item of the TPCH, as well as the item of the TPCC to part of TPCH. So because the TPCC does not contain a nation table, so we had to incorporate a nation table into the TPCC schema. And as such, we needed to introduce a relationship, a mapping between the customer and a nation, which we did as the CH using one of the attributes of the customer entity, and then finally we added the region entity. So this relates to the schema, and on the left hand side is the resulting TPC mixed TPCC TPCH schema modeled as a graph, as we can see here. With regards to data generation, we simply made use of the TPC specification for a start, and with respect to relationship cardinalities. Of course, this does not reflect the real nature of graphs because there isn't any skew. The distribution between relationships in the TPC specification is a uniform distribution. So this is subject to feature work. And the scaling, we used the scaling of the TPCC, which is based on the number of warehouses for the purpose of this hybrid graph benchmark. The workloads, we have an OLTP and an OLAP set of queries, 5 OLTP queries, which map to 5 TPCC transactions, and 22 OLAP queries, which map to 22 TPCH queries. We used execution modes as specified by the TPC. So we have a concurrent streams, concurrent OLTP and OLAP streams. And for benchmark parameters, we started with the number of warehouses because the TPCC is the base schema, and the number of concurrent mixed streams. For performance metrics, at the moment, we just considered throughput and latency. So this is a preliminary. Excuse me.
Please continue. You have 3 minutes left.
Okay. Yeah, I'm almost done. So this is a preliminary evaluation that we did, starting with an OLTP only execution, where we have OLTP streams. We keep on increasing, varying the number of OLTP streams. And as expected, at the beginning, increasing the number of OLTP streams increases the overall throughput, and until a saturation point is reached, where increasing concurrent OLTP streams decreases the overall throughput. On the other hand, because the reason for this is because of abortions of write operations with regards to concurrency control. On the other hand, for OLAP only streams, increasing it largely increases the overall throughput, although the latency of a particular OLAP stream increases, but the overall throughput also increases. This is because there isn't any abort with regards read-only streams of queries. For the varying OLTP stream, so we fixed an OLAP stream and then concurrently run OLTP streams. So what we see is increasing number of OLTP streams does not affect much the execution time of an OLAP stream. But for varying number of OLAP stream, we see there is to some extent some influence on the single OLTP stream that's been executed. So this is this is just a groundwork of our consideration of having a hybrid graph benchmark. Of course, there are things to do. So there are potential schema extensions. So you can think of it as sort of targeted for e-commerce domain. So we could extend it with feedback from customers. A customer likes a certain product and so on and so forth. And also the data generation needs to have generate data that has more real-world characteristics, and also have a metric or an overall metric, which would facilitate comparison between different systems. So this is the end of my presentation, and thank you for your attention.
Thanks, Mohammed. So is there a question from the audience on this talk? So while you're thinking, I actually have one. I mean, if I were to construct a H-step workload as biased as president or chairman of LEPC, I would maybe think of mixing SNB interactive and MBI. Was that not an option? Like running the two at the same time and see how they interact? Because
yeah,
then
exactly.
you have actually the same schema and the same data, so you don't have this problem that you have to read.
Yeah, exactly. It's an option, but so switching to the product graph domain, there was a study that a survey that highlighted that practitioners product graph is popular among practitioners, and there isn't any graph benchmark that focus on a product graph. So we thought it's an area to explore, because there isn't any existing work on it. Yeah, but of course you could use the BBC interactive.
Yes, well, that's only the syntax and the names of the entities. But is there? I mean, if your argument was that there was like a real inherent distinction regarding the structure and the complexity of the queries, but the fact that one is framed in product graph and the other in social network is just the application area, should not really affect the system per se. But regrettably, well, we are a bit short of time. But I would like to thank you for the interesting talk.